gestures.
Okay, so welcome back, everyone. So yeah, it's my pleasure to welcome Verstraete back to the second lecture. So we're looking forward to your talk.
Thanks a lot. So I'll continue with the way of trying to explain how to represent generalized symmetries on the lattice. I think this is a pretty general construction, and once you understand basically how to represent, if you understand the representation theory of fusion categories, then the physics will become very, very simple. Okay, but I have to. That's why I spent so much time last time to try to kind of argue that that representations of fusion categories are given by MPOs. So let's actually try to repeat very quickly. So we saw last time is that there is some natural matrix product. So you have a category C with simple objects A, B, and so further in C. And I have some notion of a product that is associative, and A, B, C times C. And what we figured out is that there's a natural representation of such fusion categories on a tensor product Hilbert space in terms of matrix product operators. In the sense that if I multiply an MPO A with an MPO B, that I get an NABC times this MPO C. And for the moment, I'm assuming that I have periodic boundary conditions, and these fusion rules are independent of the system size. Okay, so these are the symmetries that correspond to these generalized symmetries. Okay, so these are the ways in which you will implement the defect lines in a theory that has generalized symmetries. So for the people that have a CFT background, these are the defects. The defects will be these MPOs. Okay, so and what we ended up with was some notion of bimodule categories. Okay, this turns out to be the key in understanding topological order. Okay, so bimodule categories is like an extension of a category because it's a pair of categories. So basically, I have this was originally, I think, well, this was understood certainly by mathematicians a long time ago, but the key paper from the physics point of view was a paper of Kitaev and Kong, where they realized that you need bimodule categories to understand topological phases in two dimensions if you want to describe the edges. Okay, all the possible boundary conditions of topological phases that are non-chiral in 2D are basically described by bimodule categories, because it's not enough to have your theory, you also have to be able to describe what the edge modes are and all the possible boundaries. And that's where it sticks. But it turns out that these bimodule categories are exactly the language to describe, to find all possible MPO realizations or representations of a fusion category. Okay, for a different bimodule, you will get different representations. So these bimodules are basically labeled the equivalent of something like the different EREBs in your theory. And so what is this? I have a category C with elements, you have some kind of A, B, and so further of C. These are the simple objects in your category. And you have a module, and a module is not a category itself, because if you have a module, it's like a vector space. You can act with something on a module, but you cannot act with a module on a module. Okay, a module that's not a vector space, so you have like objects M, N, and so further, element of this module M. And then you have another category, alpha, beta, with simple objects, element of a category D. And so this is an extension of a normal category because there are new type of fusion rules. Okay, so as I said, I have like, I can have fusion rules. I can take C times C, and this has fusion rules A, B, C. But I can also act with C on M, and this it maps it to M, and this has fusion rules A, M, N. Okay, so there's different fusion rules. So again, exactly. So if I have an element in C, an element in M, I have some different, again, positive, non-negative integers that tells me how many times do I get M when I act with C on M. So there's an A, a big M. I also have an M times a D. So this other dual category will also act on M from the right-hand side. So we'll go to M, and this has fusion rules M alpha N. And then I have this category D times D, which goes also to D, and this has numbers alpha, beta. Okay, so I basically have 4 different, this is a kind of a simple generalization of a normal fusion category, but the difference is that C acts on C, D acts on D. These are 2 German fusion categories with their own F symbols. But now I will need to kind of understand the consistency equations for C acting on M and M acting on D. And indeed, so it means that if I have some line, let's call this M, pictorially what this means is that I will have a notion of acting with an element A in C on M, and this gives me an M prime. Okay, so this is the fusion rule. I kind of combine A with M and I get an M prime. Okay, but obviously you will kind of have to say there will be, I can act now with a B on this. This will again be some kind of a different thing. So this, first I have this, then I have this. But obviously, this should be compatible with the rule that if I have first B and A and M, this should be kind of compatible with this. Okay, because I know that A and B can be fused. I first act with A on M, and then with B on M, I get something. But that thing, that object, that vector, like Julien was saying, should be compatible, of course, with first fusing A and B and acting with that product of these 2 on M. Okay, and that's what introduces a new F symbol. And that turns out to be completely equivalent to these 1 F symbols that I talked about before. Okay, so that is this so-called 1 F symbol. This is a Clebsch-Gordon coefficient. Is nothing more than somehow the consistency of this kind of category. If C acts on M and gives M, then of course, if I act with C times C on M, I can do it like this, or I can do it like this. And these 2 things have to be compatible with each other. And the basis change is this 1 F symbol. It will turn out that you can realize, so this equation, if you, well, of course, now you can say, okay, what are the equations that determine 1F? Okay, it's very easy. You just say, okay, let's do this 3 times. And let's try to kind of relate this in different ways to basically this. So this kind of situation when I kind of fuse these 3 and like this, and there's 2 different paths, and you can again see that this is completely equivalent to the way that Julien kind of dealt with this pentagon equation. So there's a pentagon equation that will basically relate this to this, and there's 2 different ways. I can first fuse these 2, do this, I can first use these 2, and these 2 different ways should be compatible. And this gives me a pentagon equation that effectively involves 2 F symbols. So 1F will be equal to a 0F, 1F, 1F. And the 0F, again, is basically these are the pentagon equations. These are these F symbols corresponding purely to the category C. Okay, that means that there is some non-trivial pentagon equation that once you have 0F, you can solve for all possible solutions of this 1F. Okay, so this is 1. And then you find this. Now, it turns out that if you write this thing out in components, well, you remember in the last lecture, we talked about multiplying 2 MPLs. And if this was equal to this, it turns out that this is true if and only if there existed some tensor like this, some intertwiner such that this is equal to this. Okay, this is kind of fusing these 2, so that if the product of those things is something else, then there must be something like a Clebsch-Gordon coefficient that fuses these 2 to this representation. And that means that there exists some object here that satisfies this. Okay, and once you have this, okay, there's now 2 different ways of fusing this. You should be able, if you now take the product of 3 MPOs, there will be 2 different ways in which I can fuse these MPOs. You can first fuse the first to the third, or first the second and the third with the first. That means that there should be a relation between the way you do this and do this. And it turns out that the relation is that, again, if you write this out in components, for the examples that we had, that this object, these objects that we have here, satisfy this equation. These are effectively the 6J symbols. These are these intertwiners. But if you look at this equation, and you look at this equation, you see that they are the same. So components-wise, if you write out this equation, and you write it out in the lattice, kind of this MPO representation of this, this equation is in 1-to-1 correspondence with this one. That means that if we identify these objects with the 1F symbols, this is a solution. Okay, so if I have a bimodule category where there are consistent F symbols that satisfy these rules, somehow I can immediately construct these Krebs-Gordon coefficients that will be compatible with this. And of course, there's more F symbols that you have to define. F symbols, for example, that, okay, so there's, of course, you can do the same thing from the right-hand side. No? That will turn out that this is equal to a 3F times, okay, so this is an element in alpha, this is beta, alpha, beta, m, n. So now, instead of acting from the left, we act from the right or a module. Okay, so this is our module. Acting with these things should be equivalent to these things. This gives you rise to a new F symbol. And that new F symbol is indeed, will satisfy something like an equation for 3F. 3F is equal to 4F, 3F, 3F. And this 4F is the F symbol of the category D. And again, exactly like what happened here, it turns out that these 3Fs will be compatible with these things. Okay, this will be equivalent to this 3F times. Okay, so one-to-one, so you have this skeletal data of a bimodule category will be all these F symbols. Okay, there's many F symbols, but turns out that all these equations that have to be satisfied by these MPOs are in one-to-one correspondence with the defining equations of a bimodule category. And finally, the most interesting one is actually this one. If I have a bimodule M, I can act from the left, element A, from the right with alpha, but that should of course be again related to something like this, where I first act from the right and then from the left. And this is the 2F. Okay, so this is all data that is present in a bimodule. Okay, so it's kind of a bimodule has all this 0F, 1F, 2F, 3F, 4F. And all these things are defined by analogs of the pentagon equations. Okay, but they are mixed pentagon equations because this is 3, 3, 4, 3, 3. The normal pentagon equation is just 0, 0, 0, 0, 0. And so you solve this. So these are algebraic equations. You can actually, in practice, you can solve them. They are not too hard. But these two F symbols are exactly the F symbols that were needed to describe our MPO. It turns out that actually these F symbols have lots of extra labels, and these are exactly these loop labels that we have. Okay, so this tensor is in one-to-one correspondence, elements-wise, with all the elements of this 2F tensor. Yeah, and this is the symmetry. Okay, so this is the new thing. So these bimodule structures, they are known. This is pretty abstract. So what happens now is that, indeed, if you want to construct all possible representations, MPO representation of a fusion category, what you need to know is all the possible bimodules. You need the modules, the M's and the D's. But once you have, and specified D is actually uniquely specified because this turns out to be this an invertible bimodule. Then once you have M and C, this automatically, because of all these equations completely force that there's a unique solution of D. Okay, so there's no choice anymore. And that is basically given by these MPOs. Okay, so that means that these MPOs, indeed, so now we can construct whole families of representations of fusion categories, okay, by choosing different modules. The choice of the different modules gives me the different representations for the same fusion category C. Okay, so all these MPOs, independent of the choice of module, form representations, so they will all satisfy this rule here. Okay, independent of the module, these MPOs will form a representation of the symmetry category C. Yes?
Could you remind how this dual D category is related to C? Because you are constructing a representation of category C. This is the only input you kind of.
Yes, and then you try to find all the M's, and that gives me all the possible representations of that category.
Right, so how D is related to C?
Okay, so in the last lecture, we saw that there were different choices. So for example, if we had vec G, we could take vec here, and then this dual one was rep G. Yes. That was one choice. Another choice was vec G. Actually, I have here vec G, and then this was also vec G. This is another choice. This is actually, in this particular case, all the F symbols are equal to each other. Okay,
Right.
all this 1F, 2F, 3F, 4F, they're all equal to 0F. They're all equal in this particular case.
So the represent, because your original question is how C is represented on many bodies.
Yeah, how can I represent a symmetry C?
So for that, there are these extra D.
And it turns out that you need to find all representations. This problem is equivalent to finding all bimodules compatible with C. Wait. Yes, of course, you're right. Of course. Sorry, this is completely correct. Because these are the three F symbols. Indeed. So 3F, 3N, no, of course, you're completely right. Sorry. Okay, so, but of course, this happens now for any fusion category. You know, this game, you can play it now for any fusion category. So it turns out that there's much more interesting ones than just VEC of G. Okay? Because now we have all the consistency equations. This is just given by a bimodule category. A bimodule category is actually well-defined if and only if there is a solution for all these pentagon equations. Okay, that's the way you define a bimodule category. Say, this is a consistent bimodule category that is invertible if and only if I can find a 0F, 1F, 2, 3, and 4F that satisfies all these pentagon equations. That's the definition of a consistent bimodule category. Yes? So these are elements in the category C. These are elements in the category, in the module M, and these are elements in the category D. That's why you act from the right, you act from the left on M. Yes, okay. So in the MPO, these labels are elements in C. These loop labels are elements in M. And these vertical labels are elements in D. Yeah, that's correct. But of course, so now let's actually look at the VEC-G kind of case. Okay, let's actually look at the VEC-G case. It turns out that there are different solutions of the 0F symbols than just the trivial one. If you know the normal group theory like we did in the last lecture, this was always choosing the 0F symbol effectively equal to 1 in a trivial case. But you can put a non-trivial three-course cycle. And if you choose VEC of G, the omega, the 0F, because that's the solution of the pentagon equation, the first equation, to be this three-course cycle, and then you ask, what are the possible modules that will lead to a consistent set of equations? Then you can see if this is a non-trivial three-course cycle. Well, let's say that's, well, okay, there's some complication, but let's take the simplest example. Then the only solution of this is that you have to take VEC G here too, and VEC G here too. Okay, there is not, you cannot take VEC. It's not allowed. Okay. And this will turn out to be the anomaly. Okay, so this is like if there is an obstruction for finding different modules, this means that there's an anomaly. Okay, and whenever the module VEC, which only has one element, this is the module that has one element, is not a module compatible with your 0F symbols, you will have an anomaly, and that means that you cannot have, there will be impossible to construct quantum spin chains with that symmetry that have unique gapped ground state. Okay, because it turns out that the degeneracy of the ground state manifold will be related to the number of objects in your module. Okay, so the anomalies that people talk about, the three-course cycles, are exactly related to these kind of possible choices. What are the possible solutions of M, these pentagon equations, if I start with a non-trivial three-course cycle? In practice, actually, what happens is that this can still be different than VEC of G, as long somehow you can, like as we saw in the previous lecture, we can have VEC of G here, and then we could take G divided by H. Okay, we take any subgroup, as long as the three-course cycle acts trivially on the subgroup, then it is actually okay to do this. Okay, so it's not completely fair to say if I have a three-course cycle that I only have VEC. It's only true if indeed this three-course cycle, if this three-course cycle acts trivially like a zero, like no three-course cycle, non-trivial three-course cycle on the subgroup H, then you can actually gauge H. Okay, so that's the the little, this is just a technicality. Well, no, it's just an algebraic property. This is just the algebraic property. So you have these pentagon, you have all these pentagon equations. They are completely equivalent with all these equations that you write down for the pulling through equations for the MPOs. This is completely equivalent to these equations. And this just turns out that there's an obstruction. There's an obstruction in finding solutions. You can just put it in a computer and you see indeed there's only one solution anymore. So like there's many other categories that that don't allow for. So the one choice that is always possible is this one. That C, M, and D are all equal to C. That's always an allowed bimodule. So at least you always have one representation. One case where this is the only module is, for example, in the case of the non-trivial three-course cycle of Z2, but also for Fibonacci. Take the Fibonacci, take the fusion rules here, tau times tau is 1 plus tau. Try to find these and you see there's only one solution. There's only one module. This is equal to C. That means that there will be only one phase with that kind of symmetry. There will be no phase transition because it turns out that these different modules, as I will argue in a bit, will be related to the different phases of matter compatible with your symmetry. Okay, the different phases of matter will actually be labeled by the modules. Okay, but before we do this, let's actually talk about boundary conditions. Okay, because that's something that is actually extremely relevant in the whole discussion. Yes. Yes. Well, if it's not VEC, then let's postpone this until I discuss quantum spin chain. Yes, if you have non-trivial anomaly, then you will never be able to write down a local spin chain Hamiltonian with that symmetry that is gapped and has unique ground state. There will always be a degeneracy in the ground state. That's the anomaly in some sense. It's not possible to find a unique gapped ground state. Yes, exactly. Yeah, of course, it will be either gapless or symmetry broken. That's what comes out. It's like the Liebschulte-Mathes theorem. You can prove that with these symmetries, it's either gapless or symmetry broken, but it cannot be gapped and unique. Oh yeah, well, yes. Take a rep S3. Take any rep. Of course, you can actually convert this. Now you can start with a symmetry. Yes. No. There's many non-abelian ones that have actually different symmetries. Like we. No, I don't think so. It's really you have to solve these equations, and I don't know by heart how to. I don't know how to see that something actually has as only one possible module. I don't know, but you can solve these equations, and they are actually not too hard to solve. But anyway, so what about boundary conditions? Okay, because this turns out to be crucial in understanding these symmetries. Okay? Because as I said many times already, these MPO symmetries. Well, of course, people call them non-invertible symmetries because indeed, if you look at the range on which they act, actually, this is not a full Hilbert space. But it turns out that you can make them invertible by taking boundary conditions into account. And that's something that is, of course, not a big surprise because we have all probably looked at things like Jordan-Wigner transformations and Kramers-Bonnier. And then you see that under duality transformations or generalized symmetries, boundary conditions get mixed. Okay, so like something with even boundary conditions, anti-periodic, even charges, anti-periodic boundary conditions becomes odd charge and periodic boundary conditions. Okay, so that means that indeed, that's why it's non-invertible, because somehow these different sectors, they don't map. If you map something periodic, it becomes anti-periodic, so it cannot be invertible. But if you lift the boundary degrees of freedom to physical degrees of freedom, then suddenly these things can actually be realized as unitaries on your tensor product space. And what you have to do is actually, maybe I should use a different color for this. What you have to do is lift, okay, let's call this is this element C. We have to just add 2 degrees of freedom, like 1 degree of freedom that has the dimension of your virtual Hilbert space. So basically, this is an element in C. You also add two different. You add kind of another line in your theory that has the degrees of freedom of your virtual. And that means that there is some kind of a C here, and there's like an A here and a B here, and you try to find basically what are the conditions such that this is still kind of a well-defined theory. So basically what you want to find is exactly these topological sectors, the different sectors that give me projectors in that space by making linear combinations. So basically what the question is, so I have this object, it has an, well, actually let's do it like this. That's how I do it in my notes. This is an X, let's do it for a group. And this turns out to be G times X, because what I have here, I fuse this MPO with this MPO. So this is a 1F symbol here. And this G times X becomes GX. And then this is like unfusing again. So it turns out that this, of course, because this is periodic, this also has to be a G. What has to stand here now is a GX G minus 1. Because this MPO times this MPO has to fuse to GX. Okay, so it turns out that now you can say, let me take a linear combination. Okay, let me take a matrix that depends on X and G, sum over X and G of this. And I want to now, because these are now just matrices, no? So I know all of this is represented in terms of a tensor. Okay, these are just tensors. And I want to find what are the conditions on M, X, and G, such that this thing will be a projector. Okay, because that's what I'm interested in finding. I'm interested in finding the sectors that are left invariant under this kind of whole object. Okay, so it turns out that, well, what this means that I want this, if I multiply this 2 times, then there will be somehow a fusion rule here, a fusion rule here. I want this to be equal to itself. Okay, this gives some kind of non-trivial conditions on M. And you can completely solve this for the case of the group. So it turns out that for the case of the group, what you see is that there's an X standing here and a GX G minus 1. Okay, if this is an idempotent of your algebra, because there's an algebra associated to this, of course, X has to be equal to GX G minus 1. So that means that G has to be an element of the commutant of X. It must be part of the conjugacy class. And anybody that has looked at things like the quantum double, they know that this is something that emerges very naturally. You have to look at basically the conjugacy class of your elements. These are exactly the G's somehow commute with X. And it turns out that indeed all these tubes are basically given. If just choose an X, and this tube X is just choose element in the center of the centralizer of X. So all the elements that commute with this. And then look at a representation. Let's say nu is the E-reps of the center of X. Okay, so this center of X is itself a subgroup. Look at the E-reps of that subgroup, centralizer, and then take this object here times G times this thing, X, G, X. Okay, and these are the idempotents of the tube algebra. Okay, and these will be actually the ones that will build up this Drinfeld center that was mentioned by Julien. Okay, so this will turn out, so these boundary conditions of these MPOs are in one-to-one correspondence with the so-called tube algebra. So this is the tube algebra. And I will be interested in the idempotents of the tube algebra. Okay, and of course, these will turn out to be kind of label the topological sectors in the string nets that will have the symmetries, but it will also label the onions in your theory. And that's why somehow the full content, the onion content, the fusion rules of all these things will be related to these tube algebras. And these tube algebras are a completely central concept in understanding, indeed, all these different things. Okay, so let's, so what is interesting now, from the more abstract point of view, is that, okay, given category C, I can construct these tubes. And actually, I can also start seeing how these tubes kind of combine with each other. If I put a tube like this, but I put another tube here, I multiply these two, this will again be a linear combination of other tubes. Okay, because this is now a different, and this is how you fuse the tubes. Okay, this will give you the fusion rules of the tube algebra, and this will be the Drinfeld center, which is another category. And this category is called the center of C. the Drinfeld center of C. Nothing more than the way actually these things. I'm actually simplifying something here, because it turns out that the Drinfeld center is not about the idempotence, it's about the central idempotence. Okay, but that's a technicality that I kind of explain to the people later. It doesn't really matter for the whole discussion here. Now, what is interesting is that these bimodules, this construction of these bimodules is actually such that whenever I give you another category D, and these things are equal, then there exists a module that connects them. Okay, so this is an if and only if. Okay, these bimodules are such that whenever you have two Morita equivalent categories, which means that their centers are equal, then there will be a module M that will actually kind of connect between them. Okay, and this is, of course, there will not be a coincidence, of course, that the center of C and center of D have to be equal to each other, because it turns out that these MPOs, they will also label the possible dualities. Okay, so the different dual theories kind of will be labeled by different dual symmetries. Okay, one theory will have a symmetry C, the other theory will have a symmetry D. And therefore, of course, if there's an intertwiner that maps these theories to each other, you should also be able to map the boundary conditions to each other. That's why these centers have to be equal to each other. Otherwise, you would not have a way of mapping these things to each other. So everything is compatible with this picture. Yeah, exactly. But no. At the end, the duality will not. Okay, let's postpone this. The duality will actually be something that intertwines between a module M and a module M prime. Change the module, and this will be a completely different. Okay. Well, it's actually pretty simple now. Once you have this picture in terms of MPOs and matrices, well, like understanding what is this algebra? Well, this is just multiplying matrices now with each other. It's not some abstract quantity, no? These are just matrices that you start multiplying. So finding this idempotent is just nothing more than a simple problem in linear algebra. It's finding invariant subspaces of the algebra generated by these tubes. And that's how you can do it. So Drinfeld centers, well, the centers are nothing more, equivalent to calculating invariant subspaces of some algebras. You can do this, for example, for Fibonacci. You do this, you see that actually this whole tube algebra, the number of different tubes that you can write down, there are 1, 2, 3, 4, 5, 6, 7 possible tubes, and then you can find what are the different idempotents, and it turns out that there's 4 different idempotents. Okay. Well, there's actually 5 idempotents, and there's 4 different central idempotents. So I kind of try to find what are the, so it turns out that these MPOs project on some subspaces. Okay, like if you take periodic, if you take somehow the Krauss-Wanner defect, and you look at this as symmetry, it only has support on the even subspace. Okay, but if you allow, I would like to have support on the full Hilbert space. Okay, so what I do is introduce some extra degree of freedom that allows me to control what somehow the charge is. Okay, so this would be, with this extra tube, I have access to the full Hilbert space. And that's how these MPOs become unitaries if you include the possible boundary conditions, because then they can act on the full Hilbert space. And so the fact that these tubes are of this form, well, this is just, this is really because I have an MPO here, I have an MPO that comes here, I fuse these 2 MPOs, and this is exactly the same thing. So there's kind of a fusing of these 2 MPOs. That means that this forms them 2 of this kind, and then you can ask a very natural question, okay, what are the possible subspaces that are invariant? What are the possible idempotents in this theory? That's a very natural thing. Actually, what is not easy, and something that my students proved 10 years ago, is that indeed this tube algebra that combines these tubes is a C-star algebra. Okay, this is something that was kind of known in the literature, but using these tensor networks, you can very easily see this, that this is a C-star algebra, and indeed it's well-known mathematical results that if you have a C-star algebra, basically the only thing that matters are the invariant subspaces. So it's a direct sum of matrix algebras. You want to find these matrix algebras, and these are these idempotents. Yeah, you just have to believe me. No, okay. It just happens that this is the full Hilbert space. It has access to the full Hilbert space. It's like it's so the role of these tubes is to have basically some defect there. No? So it's a defect that would flip a spin. It's like it allows you to get kind of the charge, to change the charge. And just what you can prove is that indeed with these tubes, the support of this is really the support on the full Hilbert space, and not just on the even charge Hilbert space. So certainly by having these tubes, because you can understand what is these tubes, what is the resolution of the identity using these tubes, you can really kind of span your whole space. You can. Yes. Yes, yes, indeed. The sum of all these simple idempotents. The sum of all the simple idempotents gives you the identity. And that's basically the identity on the full Hilbert space, not just the even. Yeah. Okay. So let's try to do physics with this now. So again, I have MPOs. I want representations of fusion categories. So okay, this gives rise to these bimodules. I have boundary conditions. This gives me the full picture of all possible ways in which I can realize the symmetries, including the twists. Okay, because of course these tubes will kind of correspond to twisted boundary conditions, but you need them to kind of have the complete picture of what all of this is. So what we want to do now, well, there's two possible ways and which I could proceed. So either I could say, oh, let's now actually, before we do the physics, let's try to understand how we can do that higher dimensional generalization of this. Again, this is, I will not do this, but this is possible. So basically say, okay, what happens now if I want to have a symmetry that is actually a two-dimensional symmetry? And for this, I would not have an MPO, would have something like a PEPO, have to deal with two categories, and you can actually start cranking the whole thing and it works. Okay, so you can do this, but this is, I think the really interesting thing is to start now from the symmetries and see what are the physics, what kind of physics can I do? Yes. And the first thing that is a question. You cannot see because I have not discussed dualities yet. Okay, dualities will actually mix, they will kind of lead to a permutation of all these possible idempotents. So it turns out that the central idempotents, because Z of D is equal to C of C, the boundary conditions of one theory will be in one-to-one correspondence with the boundary conditions of the dual theory. And that's why you need to have these tubes. It's not enough to just look at the even sector. And that's why, from my point of view, this whole notion of non-invertible symmetries is a misnomer, if you take boundary conditions into account. So again, I think it's very, for me, this is kind of an important insight that if you want to understand a quantum spin system, it's not enough to understand a quantum spin system with one specific type of boundary condition. You have to understand it with all respect to all possible boundary conditions. And people in CFT know this. People in the CFT kind of community know this. If they want to understand, they want to see all their possible towers, they have to kind of look at this twisted boundary conditions, because otherwise they don't see the full operator content. They don't see the full kind of spectrum of their theory. And that's really kind of a reflection of that. Okay, but let's try to do some physics. Okay, so what we want is the Wigner-Eckert. Is it an E or an A? I don't know. Okay, we want to generalize the Wigner-Eckert theorem because that's what we want to do now. You have a symmetry. We want to construct now Hamiltonians with that symmetry. But we have everything already at hand. Okay, we have this MPO. We know basically that there is a way of fusing these two things. Then we had this rule that this was equal to this, because that's one of these pentagon equations. That means that I have, let's say, an alpha and a beta and a gamma. I just put this Clebsch-Gordon, this generalized Clebsch-Gordon coefficient. This is this 3F symbol. And I put the conjugate, and I make sure that this is a Hamiltonian, then this will commute with your Hamiltonian. Okay, so any object that I put, okay, that depends on gamma, any linear combination of x gamma times this, okay, because alpha and beta can typically fuse to many different things. So think about spin 1/2 can fuse to a 0 or a 1. Let me just enforce that gamma is equal to 0, and this will be the Heisenberg Hamiltonian, because it's a projector on the singlet. Yeah, and this completely generalizes this. Okay, so these three F symbols give me the complete theory of all Hamiltonians that commute with these generalized symmetries. So the generalized symmetries, of course, there's many more terms. I can also take a next nearest neighbor term. I can take something like this, and then fuse these two, and then unfuse again these two, and like this. Okay, and then I have alpha, beta, gamma, delta, epsilon, zeta, and I can take any superposition over these things. All these terms will commute with the Hamiltonian. So it gives me a complete set of all possible ways in which I can construct Hamiltonians. And indeed, all the examples that people have ever written down about spin chains with generalized symmetries, they can be rephrased like this. There are nothing more than Hamiltonians that are written in terms of the Clebsch-Gordon coefficients. Okay, so basically you have a Hamiltonian now. Okay, so this is sum over x gamma times O gamma. Let's call it like this for simplicity. I can simulate now this Hamiltonian. I can find the ground states. And what is somehow, how would the different ground states be related to each other? Well, they are related, so I have some kind of psi i's. And this psi I will indeed be related to the OI's acting on psi 0. Yeah, and these OI's are nothing more than the MPOs. So exactly like we anticipated, once you find somehow Hamiltonians with this symmetry and you have symmetry breaking, then all the different ground states are related to each other by acting with your O's on psi 0. Of course, it's a bit more difficult because these O's are not group-like. If you multiply two O's, you get superposition. So this is actually spanning. So basically the right thing to say is that this spans the full ground state manifold. And actually there's not guaranteed, so you have to be careful in what you choose. There's always one psi 0, so that indeed, if you act with all OI's on psi 0, this will give you the span of all the ground state manifold, but not any. There's actually some bad choices of psi 0 that you can take, such that if you act with OI's on it, you do not generate the full ground state manifold. Okay, that's different than in the usual ground state manifold. But then again, anyway, it's the same thing. Okay, symmetry breaking is nothing more. Now we identified indeed this symmetry because that's how we set up the first lecture. We wanted to understand how are different ground states related to each other. How do I actually kind of look at this? How do I calculate order parameters? Well, using somehow these ideas, we can immediately kind of understand this. So this is effectively generalizing this whole Landau paradigm. Okay, so let's actually. Oh, these O's are the MPOs, no? Oh, sorry, this is a different O. Of course, okay, this is, let's call this H gamma here. Yeah, this is H gamma. And these are the MPOs labeled by the elements in your symmetry C. These are MPOs, these MPOs that we just talked about all the time. Indeed, this H phi commutes with all these OAs. Okay, what you have is that H gamma OA is equal to 0. Well, the local terms of your Hamiltonian all commute with this because they're constructed from the Clebsch-Gordon coefficients. That's the generalization of the Wigner-Eckert theorem. And you can actually rigorously prove that this is indeed the full set of all possible. Actually, let's well, there's lots of things to say, but actually let me already connect this to some ideas that were also around in the previous talk that are interesting. So what happens actually now, you can ask what happens if I include a twist. Okay, so what happens if I have a twist in my theory? Okay, so my Hilbert space somehow spanned like this, and then I put some twist somewhere. Okay, this is one of these non-trivial MPOs. Okay, and let's actually do the twist in a very particular way. Okay, so what I will do is kind of assume that I have a finite system here, and I will implement this twist, okay, like this, but I will, because of the symmetries, I can as well write this twist like this. So basically, I introduce a new degree of freedom at infinity, and then I act with this MPO, which is now a unitary because of these tubes and all this. It turns out that this is a unit transformation like this, and I exit it here. Okay, so basically I have some ancilla degree of freedom at infinity. I conjugate somehow my whole Hilbert space by this MPO, and I leave it here. So this will be something like a system with twisted boundary conditions. And now you can ask what happens if in my theory, so I kind of create a wave packet that goes to the right. Okay, so this wave packet is just a localized object. Move it to the right. But then at some point, okay, so you have your original Hamiltonian and you conjugated it with this red line. Okay, so this is, so you have a Hamiltonian defined on this Hilbert space. On the twisted Hilbert space, I therefore kind of conjugated it with some kind of a unitary H original U dagger. Okay, this is the H twisted. No, it's not, because this is actually something that is an element of C here. So it's just a domain wall, but it turns out, and that's the whole point, that using this formalism, we can actually define topological defects. And these topological defects are the ones that you can move with unity transformations. So by acting with unity transformations, I can actually move the defect anywhere I want. Exactly. That's exactly what you have. But again, what will come out here is an ancilla. Okay, and what you have now is a new Hamiltonian. So basically, well, it's completely fair. Actually, I should have said H0 tensor the identity U dagger is H twisted. Okay, because I had to add an identity here at the end. And it turns out that these spectra are exactly the same. And now you can ask what happens if I send a wave packet in when I have such a twist defect. And what happens is once it hits this object, it will actually entangle itself with it. And what happens is that you will have somehow your wave packet that goes through, but it will be entangled with the impurity. Okay, so basically, if you have a wave packet with a system with twisted boundary conditions, with the generalized symmetries, it's very important that this bond dimension of this MPO is not equal to 1, it has to be higher than 1. And a localized wave packet, when it goes through, it will be completely transparent. It will not kind of scatter back whatsoever, because this is a topological defect. It will be completely transparent. You can just easily prove this. But what happens is that this defect becomes a non-local defect. It turns out that this solves somehow a problem that is related to a very famous problem about monopole, some kind of a monopole paradox in QFT. So Polchinski wrote some very famous papers on this 40 years ago about having chiral fermions, kind of sending chiral fermions through an impurity. The impurity kind of does not scatter and back, completely goes through. And he saw that there was kind of something very strange with the S matrix in the sense that all the particles, there was no kind of, nothing fits, nothing was right. And actually this was only solved last year by two people, Lattice and Okui. What they saw is that actually the mistake that Polchinski had made is that he should have calculated 3-point correlation function, because somehow this particle that comes in entangles itself with the impurity. And therefore, to kind of see the scattering matrix, you have to look at 3-point correlation functions. In this particular case of this very particular model with CFTs and all this and chiral fermions, this symmetry, this is a symmetry of the theory, so you don't see this string. But what we see here is that it's much, much more general. There's a much more general picture for understanding this, this monopole paradox. Basically, it's nothing more than if you have twisted boundary conditions and you have wave packets that come in, localized wave packets become non-local wave packets. And this string is actually something that could be visible. Okay? If you have a symmetry breaking, for example, this string is actually really visible. So you can easily see, construct that indeed I have a wave packet that comes in and it becomes a domain wall. Okay? That's exactly. So what you see is that using this language, you can actually shed new light on this whole puzzle. Okay? This was like a big puzzle. In terms of CFT, this is not so easy to solve. It took 40 years to solve. People thought that this is something very special that has to do with CFTs, but what you see here is it only has to do with the fact that there are generalized symmetries. Whenever you have generalized symmetries, there will be somehow the topological defects associated to them will be completely transparent to wave packets, but they will become non-local on the other side. And that's very important from the point of view of scattering theory, of course. Yes. Okay, so actually, but that doesn't have to be even, so indeed, so this is, in the criticalizing model, I have this, you can do this, but actually, okay, so maybe I should, so it turns out that this is much more general, because it turns out that instead of generalized symmetries, I will also be able to do this with dualities. and we'll have, if this is a model H, and this is the dual model here, will be obtained by this duality. Exactly the same we'll go through. You can take the paramagnetic, the ferromagnetic, combine them, to engineer the topological defect in the right way. There's only one right way of doing it. And then a localized wave packet will become a domain wall on the other side. Yep. So this is, it's much more general even than, but generalized symmetries are enough to have this effect. This is really solving in some sense this monopole scattering thing. But also dualities will have exactly the same feature. Yes, okay, so this object here, this new degree of freedom. And what is very nice is that so the degree of freedom, the dimension of the degree of freedom is exactly equal to the virtual dimension of your MPO. Okay, that's the only right choice of your impurity. So the impurity becomes somehow the virtual object. So this dimension of this MPO, this one here, the dimension that you need here is exactly the dimension that you need for your topological defect. Without that, you cannot do it. Okay, otherwise, it doesn't work. Otherwise, there will be backscattering. Okay, so this is the first application I wanted to talk about. So let's actually try to talk about a second application, namely dualities. Okay, because I've been talking a lot about dualities, but I've not explained yet what it is. So let's actually try to do this. Okay, so this is application 2. Dualities. Okay, so it turns out that using this formalism, we've been able to come up with a complete general description of all possible dualities for a certain generalized symmetry, including, of course, normal group type symmetries, including non-abelian symmetries. This is something that actually people have struggled with for a long time. What is the generalization of Kramers-Wanier to non-abelian symmetries? But actually, we immediately do it for all possible generalized symmetries. Okay, so we had this Wigner-Eckert theorem that tells you that all possible operators, all possible Hamiltonians can be written down in terms of Clebsch-Gordan coefficients. Okay, so I have a Hamiltonian, the sum over n xn times this hn. Okay, let's assume that hn is localized. Well, it doesn't really matter. These are all possible local terms. Now, if you want to know the spectrum of a Hamiltonian, and I have a certain algebra of operators that are all symmetric, it turns out that it's enough to know the structure constants of this algebra. Okay, write down all possible symmetric operators. And of course, the product of two symmetric operators is just a different operator. Of course, if this is two-body, this could be three-body or four-body. These are all included. But there's structure constants associated to this algebra. Okay, this is, in some sense, try to remember what we do when you do something like Jordan-Wigner transformation. You have a certain Hamiltonian, and I write it out in terms of creation annihilation operators, and I write it down in terms of spins, and I see that indeed the algebra of these symmetric operators fits, and then we say, oh, that's how we kind of relate spin 1/2 to fermions. Well, this turns out to be completely general indeed. So this is like this. This is an F structure constant. Turns out that if I have two different Hamiltonians with the same x, so these HNs are different, but they have the same structure constants, then these two Hamiltonians will have the same spectrum. Not necessarily the same degeneracies, but for sure the same spectrum. How can you think about this for people that are very practical and have some practical kind of knowledge about matrices? Well, indeed, think about how Langschows works. Langschows, I only have to know how to act with a Hamiltonian on a vector, and I keep on acting with this Hamiltonian on a vector, and there I can create all the possible eigenstates. Well, the only thing you need to know when I act with this thing on a vector is indeed what happens with the structure constants. So you see that indeed the eigenvalues of my theory only and solely depend on F. And now you can ask yourself, on what does this F depend? Turns out that this F depends only and nothing else on these 4 F symbols. Why? Because these HNs were nothing more than Clebsch-Gordon coefficients. So if I multiply two Clebsch-Gordon coefficients like this with each other, and I want to relate it to first multiplying this one with this one, of course, the relation between these two is this 4F. This was by construction the 6J symbol. Means that these structure constants of this algebra do not depend on the choice of module. They only depend on the 4F symbols that are purely a function of the category D, not of C, not of M. Okay, so again, we had the bimodule C, M, and D. If I choose a different M, let's call it Q, and let's call this E now, you will see why I actually call this, let's first do M prime, C prime. Okay, if I would have chosen a different module for D now, so invert the whole table now. Okay, of course, if M is a module of C and D is dual to C, then M is also a module of D, the right module. And what you see is that if I would have chosen a different category, C prime as the symmetries, that gives rise to the same D. And if using these F symbols, I would have constructed a different Hamiltonian, this Hamiltonian would have kind of other terms H. So this Hamiltonian, this dual Hamiltonian would be the sum over Xn with the same Xn's Hn dot primes. But the structure constants of these ones would be the same as the structure constants of these ones. And therefore, this Hamiltonian has the same spectrum as the original one. So this was actually, for us, this was the absolute key insight in understanding dualities. Okay, the fact that your Hamiltonian that you construct using this Wigner-Eckert theorem, somehow the eigenvalues of this Hamiltonian do not depend on the choice of module M. They only depend on the properties of D. And therefore, if I have a certain Hamiltonian, certain symmetries, and I have another Hamiltonian with different symmetries, dual symmetries, somehow these two Hamiltonians will have the same property. And it turns out that all dualities that people have ever understood, or certainly for 1D systems, are of that kind. Okay, so let's kind of write this down. So basically I have some C, I have some M, some D. This is the choice. So basically, given a certain symmetry, what we just have discussed and everything before is that all the bimodules give you the ways of representing that symmetry. Okay, so this is basically it's the Hilbert space. So this is the choice of the Hilbert space that we have here. So choosing a certain M for a certain C tells you this is the Hilbert space on which I want to represent my symmetries. Okay, that's the okay, but now it turns out that I have kind of a dual category, like this. Okay, and what we will get, what we'll end up with is actually something like a triangle. Okay, so kind of a holy trinity of bimodules. If I have a bimodule CMD, now I will have a dual theory, DQE. But if this is a bimodule and this is a bimodule, and just because this is dual to this is dual to this, then this is also dual to this, so that there's another module P that emerges. And that's just a consistency equation. So if this is a bimodule, this is one, then there's another one. Okay, so to understand actually symmetries of quantum spin systems, it turns out that this is crucial to understand this triangle. Oh, yes, yes. Well, okay. You can do it's again NPOs. It will turn out that indeed, this is a very good question. It turns out that there is some kind of a notion of there will be some new type of F symbols that you will construct. So once you have this triangle, so I have F symbols here, I have F symbols there. And then it turns out that using these, okay, this P will be something like the dual. So wait, it's D star. I have to be careful now. I forgot the exact notation, but anyway, so it is uniquely defined. Okay, so and actually it's again using NPOs, we know exactly what all these objects is. These turn out to be invariant subspaces of some intertwiners and exactly. But anyway, so it turns out that let's assume, okay, that there will turn out to be something like a non-trivial F symbol, a new F symbol that emerges that connects M, P, and Q. Okay, that is nothing more than consistency equation invariant subspaces of these things. It's a generalization of these tubes. And it turns out that using this new F symbol that once you have this triangle, okay, allows you to construct a new MPO. This new MPO has loops everywhere. It turns out this middle label is now exactly an element in P. The label here is a label M, and the label here is a label Q. Okay, so you see that this is an intertwiner that will map your Hilbert space defined here to the Hilbert space defined there. Okay, so it comes there and it maps there, because this is M and this is Q. And this is a new F symbol. It's just, again, a new MPO that is the duality transformation. Okay, so this is a complete picture of the duality transformation that will map one theory to the other one. And of course, again, you can do all the tubes and all the boundary conditions, and it's all consistent. Okay, but let's kind of try to see why this makes sense. Of course, my original symmetries in my original theory were labeled by C. Indeed, I have a way of acting with C on P, okay, because it's a module. My new symmetries on this side are labeled by D. And indeed, I can act with D on P, because that's, sorry, this is labeled by E here. Sorry, the symmetries here are E, and I can act with E on P. Okay, what is the right way of understanding now the whole kind of idea? And this is the crucial kind of insight. It turns out that there's always a unique theory E. Okay, so there's a unique symmetry E. So if I have a Hamiltonian, then there exists a unique E such that this dual theory is completely symmetry broken. Okay, that basically that's completely featureless. Okay, that's for any phase. So if you have a phase diagram, you have some spin chains labeled by these x's. Let's say this is x1 here, this parameter x2, and all these kind of things, and you just map out the phase diagram. This is phase 1 here, this is phase 2, phase 3, whatever number of phases you have. It turns out that there's always a unique duality. So for every one of these phases, there's a unique dual theory where all the symmetries, all the dual symmetries are broken. And that means that if all the symmetries are broken, in particular, there's no degeneracies anymore in the entanglement spectrum, for example, okay? Because there's no feature, there's no symmetries left. And this was something that I think for me at least was always a bit of a mystery. If you have topological phase of matter, SPT phases, all these kind of things, this is reflected, the people that know about this, in degeneracies in the entanglement spectrum. But if you, it's because there's still some symmetry left. Okay? That's the only way in which you can have degeneracies. Turns out that using this formalization, you can actually, using this formalism, you can go to unique other theory where all the symmetries are broken. And it turns out that this theory is much easier to simulate with tensor networks than the original one because all the symmetries are broken, so you need much less entanglement to do this. And it turns out that, of course, I had my Hamiltonian here that I'm interested in. Okay? And I know there's a unique E. It turns out that the MPS, or the kind of the ground state of this theory that I'm interested in, is really kind of this unique theory where somehow defined on this Hilbert space Q times the MPO labeled by P. And this is basically the ground state in my original theory. And this is how you have to label the ground states in this theory. Because at the end, I have a certain Hamiltonian. I have a dual Hamiltonian where all the symmetries are broken. But the ground state of my original theory can, of course, then be obtained by acting with my duality intertwiner on the ground states of that other theory. And so this is completely symmetry broken. So again, if I act with my symmetry E here, it generates many, many different symmetries. But I can also act with my E's on P, because E can act on P. And that means that the number of objects in P is the degeneracy. Because all ground states in my original theory can be understood in this way. This is the right way of parameterizing ground states in any theory. And this actually turns out to be, like in the case of AKLT, turns out that this is a product state and this will be the Kennedy-Tazaki intertwiner for people that know. So all the degeneracies in their entanglement spectrum are generated by this duality intertwiner. Okay, the duality intertwiner is the one that generates the degeneracies in your spectrum. Okay? And so what is the number of degrees of, what is the ground state degeneracy? Of course, it's P, okay? Because these are the different number of elements in P. This. That's why this connects now to the whole kind of point of view. That when can I have a unique gapped ground state? Only if I kind of write this down, CMD, if I can choose here to have one element, and this can only be VEC. Or it turns out that there's another choice, VEC or VEC psi. Okay, these are the two possible choices. There should be one element. So that means that I can have a unique gapped ground state of my theory if and only if the module, there exists a module with one element that kind of generates a bimodule of C. And if that's not the case, then I'm guaranteed that I cannot have a unique ground state. That's the anomaly. So this is. Okay, so what is the interpretation of this E? Okay, because you could ask, what is this category E? The optimal E that actually is completely symmetry breaking. Turns out that this E is the category of excitations in the theory. Yeah, so if whatever theory you have, think about a spin 1 Heisenberg model. I have magnons. Okay, my magnons are spin 1. And of course, magnons themselves can fuse with each other. Okay, so if you think about elementary excitations in a quantum spin chain, there must be a fusion category associated to these excitations. And this is something that is universal. Okay, this E is the same for all these. So if I'm in 3, I will have the same E independent of whether I kind of go to my original model or dual model, because the E excitations are responsible for the spectrum of my theory. Excitations, if I know how excitations fuse with each other, I can generate the spectrum of my theory. And I know that the spectra of these different theories are all equal to each other. So if I kind of take the duality transformation or not, they are equal. And that's why this E is the one thing that is the same for all dual theories. The fusion rules of the excitations is constant in all dual theories. And indeed, if I have a completely symmetry broken phase, what are the elementary excitations? They are just domain wall excitations. Okay, that means that indeed this dual theory, this optimal dual theory is actually this one. This is the theory that actually you want to simulate using tensor networks. Okay, because in this particular case, the module, so you want to have maximal symmetry breaking, you want to find what is the M here that has the maximal number of elements. And M will never have more elements than the category in your bimodule. So if you choose them equal, they are equal. So this is the optimal theory that you want to simulate that gives rise to basically your thing. And how does that reflect? How does these excitations, how do you model this? What happens in terms of wave functions? Well, it turns out, well, let's get rid of this E. Turns out that this is exactly what happens here. You put some kind of defect line E here. Okay, so you put some tensor and we know exactly what this is here and here. And this E, of course, I could pull this kind of thing through. This is exactly creating the domain wall, but I can as well kind of act it here. And I have an action of E on P. Okay? E acts on P. So if this is a P1 here, it will become a P2 there. Okay, and this is doing something that we have been puzzled for. We have been puzzled by this for 15 years. Okay, so we already know a long time ago that how to model excitations in tensor networks. We knew this, how to do this numerically, but we didn't know how to model excitations when some kind of a subsymmetry was broken. How do you actually, what are the labels of the possible excitations in a theory when you break a subsystem? It's very easy if you have unique ground state, and everybody knows that the excitations are labeled by the reps. Okay, so like in the case of the spin 1 Heisenberg model, all the excitations are labeled by a rep SO3, spin 0, spin 1, spin 2. If you have complete symmetry breaking, and the excitations are labeled by the category or the symmetry itself. Yeah, that indeed corresponds to how basically the two situations is that this is a VEC of G. In the first case, I have VEC here, and then I have rep of G. It's indeed the excitations. And the other case, I have VEC of G, VEC of G, VEC of G. These are the labels of the excitation in a completely symmetry breaking phase. But now we understand how to do this in general, how to label all the possible excitations, including the topological excitations in the theory. Okay, so let's maybe, before I move to the string nets, let's give just for simplicity some kind of a non-trivial example. Or maybe let's first do the Ising model. Okay, the Ising model, this is VEC Z2. Here you choose VEC, and then this is rep Z2. Okay, this is just the bimodule. And then there's two choices. Okay, there's two choices. Either you have VEC here, or you have VEC Z2. Okay, and it turns out that if this is VEC, then this is rep Z2, and in the other case, this is VEC Z2. Okay, so these are the two choices here. And indeed, here also have rep Z2, VEC Z2. Sorry, VEC. It's just VEC. This is. Okay, so you see that this is the phase diagram of the Ising model. It's related to all the possible bimodules. Okay, if you do the AKLT phase, for Z2, I have start with VEC Z2 times Z2. Turns out that you always choose VEC here and rep Z2 by Z2. So what is the choice? What are the possible, what is this P, Q, and E that corresponds to the AKLT model? Well, it turns out that there's some kind of a VEC psi here. And what is this? This is actually interesting. There's a psi. It turns out that in terms of the solutions of these pentagon equations, there are some freedoms to put two co-cycles in. It's not about three co-cycles. There's also two co-cycles that you can put in. And if you put two co-cycles here, because this is just a gauge degree of freedom for this bimodule, so this putting a two co-cycle is nothing more, there's nothing doing to this bimodule, but it kind of gets some two co-cycle here. And this two co-cycle has a huge effect on somehow this duality transformation, the consistency between P, M, and Q. And that is exactly what generates then the Kennedy-Tasaki transformation. And then you have here rep Z2 times Z2. And here you have rep psi Z2 times Z2. That means that this is a projective representation of Z2 by Z2 generated by the Pauli matrices. Okay, so it all fits in that kind of framework. Okay, by the way, I should have kind of, certainly this whole idea of dualities and all this is something that was worked out. Certainly the most important person was my PhD student, Laurens Lotens, but there was also Clément Delcamp and Gerardo Ortiz. Okay, so this is work that we did with them something like 5 years ago. Okay, so let's, yes. Yeah, indeed. Okay, so these are the two phases. And doing a dual, Kramers-Wannier, of course, exchanges these with each other. Indeed. So Kramers-Wannier duality will exchange the two situations with each other. And that's exactly like one of these examples, of course, where you have always a way for any Hamiltonian, there's a unique category, there's a unique dual theory where the symmetry is completely broken. If you're already in the symmetry broken phase, you don't do anything. In the symmetric phase, you go to the dual theory that will symmetry broken. Okay, so again, if you have this picture here, these triangles, the dual theory that you want to simulate is this one. Okay, so you want to change the symmetry. So if you actually want to do Kramers-Wannier, you change the symmetry from VEC Z2 to rep Z2. That's that. No. This triangle is one thing. This triangle, if I write down this triangle, where is it here? This one here. This is for one particular Hamiltonian. I have a certain Hamiltonian. There turns out that for this Hamiltonian, there is a unique category E that labels the excitations in the theory. And if I would do a duality transformation from C to E, then that dual Hamiltonian is realized like this, and this is completely symmetry broken. Yes, but that's a different phase than this one. But under the duality transformation, you stay in the same point. That's the whole point. I think this is one of these things that are very confusing because of the Ising model. For me, a duality transformation, I don't change the parameters x. I don't change them. I just change the meaning of what that phase is. Yes, yes, yes. So duality transformation doesn't change the phase diagram because it's the same spectrum. And of course, in the case of Ising, there turns out to be some accident that VEC-Z2 and REP-Z2 are equivalent. And that means that actually in Ising, typically you do a duality transformation, and then actually you change your parameters of your Hamiltonian because you do an extra, an extra rotation. But that's misleading. That's not correct. The duality transformation does not change the parameters of your Hamiltonian. This is actually misleading. The Ising model is so simple that it becomes misleading. Yeah, that's the thing. The E is the only thing that, so the E is the right way of labeling phases. Okay, that's how you should label a phase. It's by E. Because that's unique under duality. That doesn't change under duality transformations. Okay, so let's actually go to 2D. Okay, so let's try to see how we can lift now this whole formalism to do 2D physics. Okay, because at the end, all of this is about quantum spin chains. But what are these quantum spin chains and where do these symmetries emerge? It turns out that these big two-dimensional system, turns out that these MPO symmetries are symmetries of topological phases of matter. Okay, so turns out that these MPOs, they are described the edge modes. So this is the edge modes of a higher dimensional theory. That's how you get these generalized symmetries and quantum spin chains. And again, we had some objects that commute with this. No? We know that this thing is equal to 3 for this. So we can completely reinterpret this now. Okay, so basically what we can say, so this object, let's now use it to actually build a two-dimensional wave function. I will kind of use this object to build a completely two-dimensional wave function. We will immediately see how this works. I'm just doing it on the hexagonal lattice, but it really doesn't matter on what lattice you do it. Okay, so there are degrees of freedom here in this theory, okay? Because actually this is an alpha, this is a beta, and this is a gamma. And I can choose these things arbitrarily. This is always a symmetry, independent of how I choose alpha, beta, and gamma. So what I will do now is construct a tensor network in 2 dimensions where my physical degrees of freedom are labeled by alpha, beta, gamma. I just leave them open. I just say, look, it's alpha, beta, gamma. Let me actually kind of say that I have a wave function now that lives in it's a tensor network in a 2D space that extends everywhere. And locally, my physical degrees of freedom become somehow the labels of my category D. Okay, so this category D, it's the labels alpha, beta, gamma, and so further. That will form my Hilbert space. And obviously, there are some non-trivial fusion rules associated to this, like this times this must fuse to this. And these are the vertex constraints of your string net. Now, what is fantastic, if you kind of write down an MPO like this, or a tensor network like this, because now I have a 2-dimensional extensive system, it automatically inherits, of course, all the MPO symmetries. If I have an MPO symmetry that is like this, I can just deform it because of this rule. Okay, if I have an MPO, I can just pull it through, like something that acts here, I can act there, and so further. So we can move these lines arbitrarily. And that's why these MPO algebras that we have been talking about before, of course, are the symmetries. They are the hidden symmetries of the topological phase of matter. Turns out that these things are the most general way of handling string nets. So how do you construct the most general string net? Take a category C, choose a module M, solve for all these pentagon equations. Here, this is a 3F symbol. Construct these 3F symbols, use them to construct your string net. Okay, so that means that actually we not just have one string net here, we can of course construct a whole family of string nets. For every different module, we'll get a different string net. Okay. And these string nets will kind of all be equivalent. And these string nets have automatically all these MPO symmetries. Okay, so these are really the defect lines that people say. So this is a very explicit way of understanding the defect lines. Okay, and also immediately you see that if I cut the system open at the edges, the degrees of freedom are of course given by these MPOs. So you see that the degrees of freedom are now labeled by these M's. It's exactly how we constructed our Hilbert spaces. And that's exactly what Kitaev and Kong did. They realized that the boundaries of string nets are given by bimodules, and these bimodules are labeled by M's as the degrees of freedom on the edge modes. The quantum spin chains, nothing more than the edge modes of your. Okay, but let's kind of put this now on a torus, like Julian did. Let's try to understand what are the topological sectors in this theory. If I kind of take such a string net now, and obviously I can take MPO symmetries and I can wind them like this, and I can wind them like this, and they cross at some point. Now it's a very easy exercise to see that actually these tubes that we defined as the boundary, the edges, the boundary conditions for the MPOs will be in one-to-one correspondence with the topological sectors. Okay, so the symmetries, somehow these boundary conditions that were given by tube algebras are nothing more than they are labeling the topological sectors in your theory. What is more, if you have your string net, well, it doesn't matter like this. Turns out that the anions will be, just change one of these tensors to another tensor with a string attached to it. What do we have to put here such that this is an exact eigenstate of the Hamiltonian? I've not talked about the Hamiltonian, but of course there's a Hamiltonian for this. These will exactly also be the tubes. Okay, so exactly the same tubes will be the anions in the theory. It will actually label the anion kind of objects in your theory. And you want to know things like topological spin. Well, topological spin of an anion, okay, all of these are tensors, no? They're not just abstract things, they are actually tensors with labels. The only thing you have to do is relate this object. It's e to the I5 times this object. Turns out that they are proportional to each other. The proportionality factor is nothing more than the topological spin. All these things like braiding, they all come out directly out of this representation. So one thing I want to say is, so once you understand the representation theory of categories, you immediately have access to all these things. You immediately understand topological sectors, string nets, boundary conditions, topological spins. They are very, very tangible objects that you can do. Okay, so I see that I have 2 minutes left. So let's now actually play 2 last minutes. I want to actually construct an explicit mapping between these TFTs that we have now and actually lattice versions of CFTs. I want to kind of use this formalism now to construct critical partition functions. So you see here is I have a string net, and this string net has automatically, independent of what these degrees of freedom are, they have these topological defects that are kind of symmetries of the system. Okay, so to get a critical partition function of a stat-mech model, what I need is exactly something like this. I need some partition function with tensors everywhere, and I want them, but there's no physical degrees of freedom. If I look at the classical stat-mech model of the Ising model, okay, this is just a number, the partition function, but the partition function is, of course, actually a tensor network. Okay, so like the Ising model can easily be written down as a tensor network, and if it becomes critical, it turns out that it will have new type of defect line symmetries. Exactly these defect lines that are labeled by these MPOs. So what I want is a classical partition function with MPOs that I can move at freely. Okay, these are the topological defects in the theory. So how do we do this? Well, it's actually completely trivial. I take the string net, and I take the overlap with the well-chosen product state. Or actually, it doesn't have to be a product state, but any state. So you basically have a string net. It's a 2+1 theory. I just take the overlap of that string net with a product state, a well-chosen product state. And independent of this product state, this theory is a stat-mech model that has the defect line symmetries. It turns out that all exactly solvable stat-mech models that are critical are of that form. You can relate them to this construction. And that means that this construction really separates the topological part from the geometrical part in your theory. And that's something that is actually pretty, I think, very powerful. And I think this is actually very nice. And we call this the strange correlated construction. Okay, so this is certainly related also to the SymTFT. It's not entirely clear what this means, but this is somehow much more explicit than what people do in a SymTFT. So we really kind of, starting from a TFT, we are able to construct critical lattice models with all the possibles. And using this formalism, well, there's lots of conditions. We can actually construct new type of critical theories. So like we constructed a CFT that was not known. That is probably the H group CFT. And so you can start playing all kinds of games. This seems to kind of allow you in a very constructive way to implement a program that was actually envisioned by Jones, okay, the famous Jones from the Jones polynomial. He always had the dream of understanding StatMech or critical systems starting from a TFT perspective, from the perspective that it's the topological part that matters. Using this formalism, you have an extremely explicit way of starting from a purely topological phase at zero correlation line and relating it to an actual classical StatMech model that is critical. I think I have to stop here. Thanks a lot for your attention. Well, if you have the CFT data, in some sense, I think you should get indeed the symmetries of this thing, which is kind of given by the category C. Using category C, we should be able to construct this. But of course, in principle, it's not clear that this StatMech model that you will get here will correspond to the CFT that you want. What it could be is that actually a coset theory. And that's typically what happens, is that there's some kind of implicit condensing going on. By putting this thing on the lattice, you get another CFT with the same defect line, symmetries. But typically what you get, and that's a conjecture, is that the critical StatMech model that you get is the CFT with the smallest central charge that has exactly this symmetry category C. Okay, and this can be obtained by actually condensing or kind of by having coset theories and all these kind of things. I think it's still an open question what is exactly going on there. But that's a very good question. Yeah, that's a good question. So probably yes, by just choosing, but it might be that you actually have to start from a bigger category C, something that is embedded, and then that one, because there's more constraints, will actually flow, will not have kind of relevant or marginal perturbations, so that it will actually flow to the right thing. But I think this particular question that you ask is open. Right? Just we know that we get critical models, but exactly kind of what, if you want to invert the whole problem, that's still an open question. Yes. No, I used some symmetries, and I used the Clebsch-Gordon coefficients of these symmetries to construct wave functions that have these symmetries. Yes. Well, no, but much more. No, I can perturb these string nets because I can do anything I want. I can actually put anything on top of that. It's not just the string net that has this property. Actually, the perturbed string nets will also have all these symmetries. No, but okay. So these symmetries are the symmetries of the non-chiral topological phases of matter. Yes, the non-chiral ones. Okay, so the open problem, as Julien was also saying, is what happens actually with chiral theories. For these, we don't know what the symmetries are. Okay, again, so what is so it's the symmetries of this string net. This is called the input category. Is a category C. The content, the operator content, or the onion content of this theory is the center of that theory. Okay? And that center is modular, satisfies one of the rules that Julien talked about. Okay, so the center of the category that corresponds to the rules of Julien. The input category does not have to be modular. It can be any category. It doesn't matter. Any fusion category will give rise to this. Okay, so, but this is a general construction for kind of understanding string nets, the symmetries, edge modes, excitations, and actually also for simulating them on a computer. But of course, there's more, because in principle, there's a whole story that is completely independent of this, that is about spin chains. And it's really classifying all possible spin chains with all possible symmetries. And something that is actually extremely interesting, and this is that emerged out of a discussion with Liang Kong, is that, so he was always puzzled why actually quantum spin chains can have a categorical symmetry. Because he says, if I have a categorical symmetry C, that is chiral, this doesn't make sense. This can only exist if I attach this to a certain bulk where I have anions in a theory center of C. So he says that a theory C can never occur on its own. You always need also the center of this C to be attached to it for this theory to be consistent. But that's exactly what somehow these boundary conditions do for you. Okay, so if you have a spin chain, yeah, and then you kind of look at all possible boundary conditions, this is the center. So this is labeled by C, but the center of your theory is actually the one that plays the role of these idempodes. So the center is realized by the possible boundary conditions. And that's another reason why you should always look at the spin chain together with all possible boundary conditions, because then you have your theory and the center, and that's a theory that is actually well-defined and consistent. Yes. Yeah, indeed, they are the one-form symmetries of this 2D system. Exactly. Exactly. And then there's a very systematic way now to go to StatMech. And that gives you very so this is the reasoning. No, you have spin chains that might be critical or not or whatever. These are with these MPO symmetries. Using this, we can construct string nets, but then with this strange correlator construction, we get back StatMech models in 2 plus 0. So this is a 2 plus 0. So this thing on the left, so we have a 1 plus 1, we have a 2 plus 1, and we have a 2 plus 0. And all these theories have the same symmetries. Okay, so these are quantum spin chains, these are StatMech models, these are string nets. Okay, and using this kind of mapping, you can understand that all of them are kind of the essence of these theories, all the properties, all the basic interesting properties are kind of related to the fact that they have exactly these MPO symmetries that are represented by bimodule categories. Yeah, but on the lattice. Yes, on the lattice, we don't know how to construct chiral CFTs. No, it's not clear because you actually, what is very important for the StatMech is that these bond dimensions are finite. And we don't know how to realize chiral theories with this framework of tensor networks. So there is probably some reason why it's impossible. You cannot kind of realize with the finite state spaces, you cannot realize chiral StatMech models. So it's consistent with this. Yes, it doesn't give you the degeneracies, only the eigenvalues. Yes, no, the point is that if I have a Hamiltonian that is a sum of many local terms, there's only one thing that determines the eigenvalues of H, and it's of course these coefficients xn, and the structure constants of this algebra. And the whole point is now that if I have, so that means, and these structure constants only depend on D. Therefore, if I take a different module for D, then this kind of dual theory with symmetry E will have the same eigenvalues as this theory. And that's a duality. These are dual theories. But they're very non-locally connected to each other. No? So there's these transformations between one, and the other one is very non-local. It's given by an MPO. Another MPO is exactly this MPO here. Or this one here, actually.